Everybody have a look up at the board right now. Tell me what you see. Okay. Sometimes we call them contrails or condensation trails. The condensation trails that follow airplanes. You said crossing each other. So how many jets or planes would you have? Okay. We got two airplanes here crossing each other at almost 90 degrees. Did they hit each other? No, they didn't collide with each other, right? What else? Two airplanes, 90 degrees, almost 90 degrees to each other, didn't hit each other. Yep. Okay, one passed more recently. Which one is it that passed more recently, number one or number two? Number one, okay, so one is more recent, good, and you know that because the condensation trail isn't as diffused, it's not as spread out, right? Okay, makes sense. What else? Look at diagram number one or airplane number one. How many engines does airplane number one have? Probably two engines. Maybe diagram number two or plane number two does as well, although it's a lot harder to tell on that one, right? Because it was in the distant past or a little bit more distant past. Can you tell which way they're moving? Looks like number two is going this way, right? Number one, it is harder to tell which way it's going. I think it's going this way. Yeah, because the contrails are spreading out over time. So I think it's going this way, although we know with a high degree of certainty that number two is going down and to the left. Look, I asked you one question at the beginning of this little lesson. I said, what do you see? And you guys told me about airplanes and trails that followed airplanes and how many airplanes there was, which way they were going, if they crossed each other, how many engines they have, okay, which one was more recent. And like you told me all kinds of stuff about these two airplanes without ever having seen either one of the airplanes. With indirect observations, you were able to tell me a lot about those two airplanes that I never told you. I never told you there was airplanes here. You told me that in the beginning. We use this as an analogy to describe how we can detect subatomic particles. Today we're going to talk about, well, subatomic particles, but I sometimes call them sub-subatomic particles because we're not talking about protons and neutrons and electrons here. We've observed protons, neutrons, and electrons. We don't need anything more about protons, neutrons, and electrons. We want to know what makes up protons and neutrons. What are the components of protons and neutrons? How are we going to find out about that? Well, how about we take a couple protons, we accelerate them to crazy high speeds, crazy high kinetic energies, and then we smash them into each other. And we do that to overcome the forces that exist within them. It's like in a parking lot, you got two cars hit each other at 6 kilometers per hour. What happens? Maybe you dent the cars a little bit. Maybe you scratch the cars a bit. If you want to find out what makes up the car, you got to crash them together not at 6, but at 160. Two cars coming towards each other at 160 collide head on, and what happens? They pretty much disintegrate, right? The kinetic energy that they possessed because they were going so fast was enough to overcome the bonds that kept the car together. The bolts, the screws, the welds. We overcame those bonds, broke the car apart into a million pieces, and found out what it was made out of. If we accelerate these protons to crazy high speeds, just like the car's going at high speeds, we'll break the bonds and overcome the internal forces that keep them together. But once we break them up, there's little tiny particles, little tiny charged particles that are generated, little tiny charged particles that make up protons and neutrons that are generated. But how do we see them? Can't even see a proton, for heaven's sake, let alone something that makes up a proton. This is where the indirect observation comes from. This is where we observe indirectly things that we can't actually see. Two ways that we're going to talk about. One's called a cloud chamber. In a cloud chamber, we have air that has got all the dust taken away. It's pretty clean air that's super saturated with water or alcohol. So it's basically, we're saying it's ready to rain, water or alcohol, but it's still a gas. It's a gas, but it's almost a liquid. The gas is almost a liquid. Now, when we smash these protons together, we got what I call sub-subatomic particles that are charged particles, sub-subatomic charged particles. Remember, that's my name for it, sub-subatomic. It's things that are smaller than protons and neutrons. Sub-subatomic particles that are charged, that we get out of it now, that we can't see, but that ionize these molecules. And then these ionized molecules cause the vapor, the gas, to condense into a liquid. So through this process, the gas that we had that was almost a liquid ends up condensing into a liquid. The condensation. Now we don't have to observe these tiny little sub-subatomic particles that we call quarks. We just have to observe the cloud trail or the condensation trail that follows them like this. We didn't have to observe the airplanes. We just observed the condensation trail that followed the airplanes, and we were able to determine a lot about those planes. Now there's another way we can do that as well. It's kind of the opposite to what we just described. Call it the bubble chamber. In the bubble chamber, instead of having a gas that's almost a liquid, we have a liquid that's almost a gas. The liquid is just below the boiling point. We smash these particles together, breaks up into these sub-subatomic particles, or quarks. These sub-subatomic charged particles ionize molecules. And then these ionized molecules, they don't cause gas to condense to a liquid, they cause liquid to boil into a gas. So instead of having gas transforming into a liquid or condensation, we have a liquid transforming into a gas, or we have evaporation. Here we follow the condensation, or we follow the clouds, which is really what condenses. That's a cloud, right? We follow the cloud. Here we don't follow the cloud, we follow the bubbles. This one is like the airplane, right? Following the clouds behind the airplane, or the contrail behind the airplane. This one is like following your little brother or sister around the yard when they got one of those little toy lawnmowers that has the bubble maker on the side, right? And as they walk around the yard and the bubbles come out with that little toy lawnmower, you know what I'm talking about? You don't actually have to see your brother or sister to know where they are. You can follow the bubble trail. You see these bubbles coming from this line. Hey, I know where to look for my brother or sister because I can follow the bubble trail. Now, realistically, what we do here is add a magnetic field, add an electric field, change the magnitude of the electric field and the magnetic field, you change the direction of it, manipulate all types of things to try to change where these sub-subatomic particles or quarks go. We end up getting patterns that might look something like this. This is exactly the same thing as you see right here. Just a little bit more complicated, that's all. Just a bit. Okay. We could do some calculations with this if we had some numbers for magnetic fields and radiuses and so on and so on. Okay. But the gist is the same as following the cloud path that comes from the airplanes, the two airplanes that we had. All right? So what have we learned about these particles? There are two general categories of particles. There's what we call the fermions and the bosons. We're going to focus on the fermions, but I'm going to really briefly tell you what the bosons are. They are particles that are what we call force carrier particles. Particles like photons, we're familiar with that, a gluon or a graviton, or some of you may have heard last couple of years, we've finally observed the Higgs boson that used to be theorized to exist, being responsible for mass. Now we know that to be the case because we've actually observed it in the last couple of years in the Large Hadron Collider. These bosons are force carriers. They're not particles that make up atoms. They're particles that glue things together, that keep things together. Now, we're going to focus more on the fermions, or we're going to focus entirely on the fermions, of which there are two types. The first type is called a lepton. A lepton is a fundamental particle. It does not get smaller than a lepton. It's a fundamental particle that is not mediated by the strong nuclear force. In other words, the strong nuclear force doesn't affect a lepton. You guys remember the strong nuclear force? We talked about radioactivity. There's the electrostatic repulsive force, the strong nuclear attractive force. The strong nuclear force doesn't affect leptons. These fundamental leptons. Some examples of leptons would be an electron or an electron neutrino, a muon or a muon neutrino, or a tau neutrino. We need to remember these. We need to remember that an electron is a fundamental particle that is not mediated by the strong nuclear force, as well as the corresponding electron neutrino. Hey, by the way, whenever we talked about beta negative decay, it was always a neutrino produced, right? Sorry, beta positive decay and neutrino produced. That was an electron neutrino that was produced, not a muon or a tau neutrino. We just dropped the word electron because that was the only kind of neutrino that we learned about. Whenever you hear neutrino, for us in physics 30, it's an electron neutrino. By the way, the antiparticles of those are also leptons. What's the antiparticle of an electron? Quick, antiparticle of an electron is a positron, and the antiparticle of an electron neutrino would be an antineutrino, right? An electron antineutrino, which is the thing that's produced in beta negative decay. Now, the other type of fermion is what we call a hadron. Hadron is a particle that is mediated by the strong nuclear force. It is affected or controlled by the strong nuclear force. Hadrons are made up of smaller particles that we call quarks. So they're not fundamental particles. Now, these quarks can arrange themselves in different ways to produce different types of hadrons. The type of hadron that we're concerned with is the baryon. The baryon is made up of 3 quarks, specifically a combination of up and down quarks. There's 6 types of quarks, by the way. There's the up quark, there's the down quark, there's the top quark and the bottom quark, there's the charm quark and the strange quark. We need to be able to deal with the up and the down, because the up and the down quark, combinations of 3 of those make up baryons, which include protons and neutrons. Now, a proton is made of of 2 up quarks and a down quark. A neutron is made up of an up and 2 down quarks. I want you to check your data sheet for just one moment here. Go to the bottom right-hand corner of your data sheet. You're going to see that the charge of an up quark on your data sheet is plus 2/3 of the elementary charge. And the charge of a down quark is negative 1/3 of the elementary charge. I'm going to circle that because you need to be familiar with it, but you don't need to memorize that because it's on your data sheet. If you try combining these 3 quarks at a time, proton up, up, down, up is 2/3, up is 2/3, down is 1/3. What does that add up to give me? 2/3, 2/3, negative 1/3 is 3/3, or 1. 1 elementary charge is the charge of a proton, right? What about a neutron? Up, down, down. Up is 2/3. Down is negative 1/3. Down is negative 1/3. 2/3, negative 1/3, negative 1/3 gives me 0, which is the charge of a neutron, right? It's neutral. Is that okay? Now, I am going to show you the one more thing, but I'm done circling things. So I'm done telling you what you need to remember. But remember, these hadrons are made up of two subcategories. One's called a baryon, the other is called a meson. And an example of a meson, which is made up, by the way, of a one quark and an antiquark, so two things, as opposed to the baryon, which is made up of three things. An example would be something like a pion. There's other particles that we don't have listed here as well, but they fit into these categories.